So let's go with paper one of my PhD thesis that it's named Performance of a Two-Dimensional Hydraulic Model for the Evaluation of Stranding Areas and Characterization of Rapid Fluctuations in Hydropeaking Rivers. It contributes to Objective 1, demonstrating how high-precision lidar data can enhance 2D hydraulic modeling for quantifying environmental impacts and propose alternative operational scenarios. So in this reach, we can see here in the right, the point cloud of the lidar bathymetry. So we find this was the first LiDAR dataset that I ever got. I was still much younger than now. I think it was like 8 years ago when I got it for my master thesis first, and then we continued through the PhD. But if we found like great amount of data, that means that we have the plane that measures with the sensor, and we could even get points in the ground of a density of 20 points per square meter. So you can imagine this, like every square meter has 20 measure points with the altitude. So it's a really dense data set. And what we want to do in this paper is evaluate how good can perform the 2D hydraulic model with that calibration and using it for quantification of stranding areas. And in this paper, stranding areas mean where the fish will be stranded, where the fish will be without water. So we quantify stranding areas as the dry out areas. Even though this might not be exactly the case, but for a simplification and to be able to do it with this model, we say, okay, the areas that are going to get dry are going to be potential areas for stranding for fish. So what's this thing of hydropeaking, no? Because I am saying what are this thing of rapid fluctuations in hydropeaking rivers? Here we find the classical, I'm just gonna move myself so you can see better. We have the classical scheme in which we find upstream here a lake, and this will be the natural path that the water will flow if there was no structures, if it was completely natural. But we humans use hydropower and we build dams like the one that is here to increase the reservoir capacity, increase the volume of water that we can regulate. And we divert the water through tunnels. All this red line is an underground tunnel, maybe around 8, 10 kilometers long, all the way down here to the power plant. Because if you know, hydropower uses the force of water, the amount of water that we have, but also the altitude. So by doing this full tunnel, what we can use is a lot more of the head of the energy that the water has because of the altitude to produce larger amount of energy. So in this area down here, we find a strong fluctuations in the flow. Strong fluctuations in the flow. What does this mean? It means like the hydrograph looks something like this. This is a hydrograph that goes from September 2 to September 14th. And what we observe are what we call peaking events or hydropeaking events that are all these big fluctuations. And this happened because they decided to turn off the power plant. And then it's like open and closing the tap at home, right? When we decided to open to produce more energy, it creates an increase in the fluctuation. If they close because we don't want to use more energy, it produces a strong decrease in the flow. So this is thing that the actual environment is not used to, these big fluctuations in the flow discharge. So that has an impact in fish. And we will see more about this, but I also want to show that this is we actually look through the whole many years data set, and we could quantify that the number of rapid increases has a peak between 6 and 7 in the morning. That means that one of the times that we open the tap, that we open the power plant, is either at 6 or 7 in the morning. That happens because it is the time when everyone wakes up and you start to using your energy, turn on the lights, turn on all the mechanisms at your house, and we start to use up. If we observe the curve of the energy demand between 6 and 7, is when we have the strongest variation. And look, because it's not the biggest need of energy that is actually at 8, 9, it's the biggest fluctuation, the steepest ramp. And this is really interesting because hydropeaking or hydropower comes here to the game to compensate for these small fluctuations because we cannot exactly know which minute the people will need the energy, but we need to produce the same amount that is consumed. But because it's changing so fast, hydropeaking comes into the game to regulate these small variations. And this is the renewable energy generation sources in EU. So what can we see in this graph? That solar, hydro, and wind are the main source when it comes to renewable energies. We know solar and wind are increasing a lot, and we cannot choose when the sun shines, and we cannot choose when the wind blows. So that produces strong instabilities in the system. All of a sudden, the sun, it's a lot of energy, but we don't need that much energy. Okay, hydro peaking can close. That's one of the super big strengths in hydropower, that it can produce whenever we need it to stabilize the load. And this is, we have talked a lot about this in Spain because we recently had a blackout. And some people say it's about the solar, some people don't. It's actually a very complex problem, but I'm not going to say it was a cause of sun or wind, but I'm going to say that hydro is really making a big share in Europe in general in stabilizing the load of the full energy production and also hydro peaking. So that's why we study these effects, because they are going to become more and more important as sun and wind and as energy sources are increasing. Hydro peaking will need to step up to balance the load of the energy market. And that affects the environment. There is this paper that is the impact of hydropeaking on juvenile brown trout, Salmotruta, in Norwegian regulated rivers. Maybe you can read down here. It was written by Salvate and also myself somewhere there. And they study by actual field measurements the density of fish per square meter at different localities in 2016, 2017, 2018. In Estorane, you can see this river. These are the two of them doing the actual measurements. And these are the results. I'm going to put myself here for showing you better. So these are the results. And what do we see? We see okay, that stations R1, R3 are on the bypass ridge above the power plant. You see station R1, R2, R3 that are measurement stations are below of the power plant. The flow is going this way, no? So when they measure upstream of the power plant, they find two things. That the young of the year, in the up graph, the young of the year, that is the fish that is smaller than a year, uh, are present, and also the older fish are present. That means that the fish managed to survive. We have both young fish and we have both old fish. But on the contrary, if we observe station H1, H5, we observe young of the year, so-called baby fish or small fish that is smaller than a year, but the older are gone. So that means that we do find a difference in the presence of older fish when it's located downstream of the power plant, meaning that the actual power plant and its fluctuations are affecting the survival of the fish. So We did a model, we calibrated, and we ran many hydrographs that you can see here to quantify the potential critical areas where residual flow conditions have ecological impacts. If you look at the hydrographs here that you can see, yeah, I'll put myself here. We studied different, like going from 3 turbines to 2 turbines, 2 turbines to one, from 1 to 0. The residual flow, it's 6 cubic meter per second. So the ecological flow or the minimum flow is 6 cubic meter per second. And then we especially studied this residual flow. And this is, for example, the map that we got for a velocity of 6 cubic meter per second. We observe that all these dried out areas, the areas in red, match areas where stranding of fish have been observed. And this is great because then with a visual effect, we can see, okay, what are the areas that are going to be potential areas for fish stranding. We can have a very quick overview and evaluate that. And also, if we observe, for example, in Yerdeoine, in this middle island, this side channel nearly dries out and becomes stagnant with velocities below 0.05 meter per second. This model helps us to say, okay, this side channel is like completely dead almost. If we go to residual flow, this is not going to be a suitable place for fish habitat, even though like good ground gravel bars might have been observed and it's a place where actually fish come to spawn or to put their eggs. Yes. This is an example of a shutdown scenario. That means this is a model where we shut down in 5 minutes. So the power plant shut down from 66 cubic meter per second to 6 cubic meter per second. And from this model, we did several studies to study how rapid this happens. So we'll go to the next. In this graph, I'm going to make myself a bit bigger for this. In this graph, we observe different things. So if you can see the graph here down, we observe point 1, 2, 3, 4, 5, 6, 7, 8. And for each of these points, we compute the water surface elevation for two cases. For a scenario A here in the left, that is the hydrograph shut down in 5 minutes. And a scenario B in the right, that is an alternative shutdown scenario in which the power plant shut down in 30 minutes. Each of the turbines shut down in 30 minutes, meaning that we have a much smoother shutdown. So also I want to say something here. If you observe this hydrograph, they are not a straight line. It's something like this. And this is because the turbines have some mechanical constraints that the actual 5 minutes have to be a shutdown rapidly scenario. So what do we see here? Anyways, that for the actual scenario in which everything is shut down in 5 minutes, we have very strong variation, more than 10 centimeters each 5 minutes. For example, are the areas in red. While for the alternative scenario, these red areas are much more reduced. But we can quantify that. And the way we wanted to quantify that was by measuring, and I'll put myself back here, was by measuring the dewatering ramping rate that we can see here, the dewatering ramping rate. The dewatering ramping rate is when the water surface elevation decreases and which velocities this can happen. Because according by the handbook of the environmental handbook, that is a publication, a little book of recommendation by Bakken et al. There are these ranges proposed that this dewatering rate is small if it is between 0 and 5 centimeter per hour, moderate between 5 and 13 centimeter per hour, big if it is more than 13, very big if it is more than 20. So we observe that for the shutdown scenario in 5 minutes, the dewatering rates are very big. While for our alternative dewatering scenario, that is this one in 30 minutes, We find two things. First, that the first 25 minutes, the dewatering rates are really decreased, but that these last 5 minutes that have been to shut down suddenly because of the hydropower mechanical turbine constraints, the watering is still quite big. So that means that these mechanical constraints still might have an effect in the river. To wrap up all this information, what we could say from this paper is that the hydraulic model in combination with the LIDAR data was really good in the quantification of dry out areas, quantification of the wetted areas, quantification of depths and velocities in the river to see which are the most suitable places for fish and that should be maintained. But also it was great to quantify and model all these alternative scenarios. And that's it from paper one. I'll show you more later in paper two. Bye bye.